We finally made it to the fundamental theorem of calculus. This is the theorem that changed the world. When Isaac Newton and Gottfried Leibniz created calculus, the creation of the definite integral and the indefinite integral and their relationship transformed the world. Up to now, if we wanted to find the value of a definite integral, we had to use a geometric formula, such as the area of a circle or a triangle or a trapezoid. But this is not a good way to find the area between a curve and the x-axis. We need a better way, and the fundamental theorem of calculus provides that. The fundamental theorem is divided into two parts. In the first part, we'll need the mean value theorem for integrals in order to prove it. In the second part, we need the regular mean value theorem. As I said, the mean value theorem is a foundational theorem in mathematics. Fundamental theorem of calculus is the foundational theorem in calculus. Let's take a look now at some of the learning objectives in this section. We're going to first describe the mean value theorem for integrals. We need this theorem in order to prove part one. Then we're going to explain the fundamental theorem of calculus part one. Now, I'll be honest, we don't use part one as often. In fact, it's fairly rare until you get into more theoretical mathematics. It is an underlying theorem, and its results get used a lot. We'll also use the fundamental theorem of calculus to evaluate the derivatives of some integrals written in definite integral form. Then we'll learn about the meaning of the fundamental theorem of calculus part two. This part of the fundamental theorem of calculus gets used constantly. From now on in calculus, you'll be doing derivatives and using the fundamental theorem of calculus part two almost constantly. We're going to use the second part of the fundamental theorem to evaluate definite integrals. This is our better way of calculating the area between a curve and the independent axis. This will give us the relationship between antidifferentiation and the definite integral, and it explains the relationship between differentiation and integration. Let me share my screen with you so we can get started. We start with the mean value theorem for integrals. Now, to remind you, the mean value theorem says that if you have a function that is continuous and differentiable over an interval, and you connect the endpoints of the interval with a secant line, somewhere between those endpoints, there must be a point where the slope of the tangent line is equal to the slope of the secant line. Now we want to take a look at the mean value theorem for integrals, which basically says that if you have an integrable function over an interval, then somewhere on the interval, it takes on the average value of the function. Let's take a look at the statement of it now. One way to conceptualize this theorem is with velocity. Velocity is a continuous, undifferentiable, and integrable function. And it implies that if your average velocity between two toll booths was 85 miles per hour, then at some point you had to have been driving that average speed of 85 miles per hour. And that's why you get a ticket on a toll road without any radar present. Now, the formal statement starts, of course, with a continuous function. Continuity is one of the most important concepts that we have for theorems. It provides the condition that allows the theorem to be proved. The function needs to be continuous over a closed bounded interval from A to B. then there has to be at least one point C, but this time in the closed interval, not the open, as in the regular mean value theorem. And somewhere in that closed interval, the value at C is the average value of the function. Remember that the definite integral from a to b of f of x dx gives us the area between the curve and the x-axis. Dividing by the width of the interval gives us the height. And that becomes the average value. In other words, if I were to draw a horizontal line at the value of f of c over the closed interval from a to b, it would have the same amount of area as the area under the function f over the closed interval from a to b. Let's go ahead and prove this mean value theorem for integrals now. We know that we're starting with a continuous function on a closed bounded interval, which means we can use the extreme value theorem. We're guaranteed that there must be an absolute maximum, uppercase m, and an absolute minimum, lowercase m, on the closed interval from a to b. It's either at a critical point in the interior, or it occurs at one of the endpoints, A or B. There has to be a maximum y value and a minimum y value. This implies that for all the x values in the interval between A and B, that the y values are between the absolute minimum and the absolute maximum. They could be equal, but they have to be between. There can't be a y value that's lower than the minimum or higher than the maximum. Then, by the comparison theorem for integrals, we know that if we take the area under the curve and we take the maximum over that interval and multiply by the interval, this gives us a rectangle at the maximum value. And if we take the minimum value times the width of the interval, it gives us a smaller rectangle at the height of the minimum. Let me draw a picture just to remind you of what this is doing. Let's suppose again that we have an interval from A to B, and we have a continuous function on A to B. Probably I need to draw a better function. There we go. Now, we know that the center part of the inequality is giving us the area under the curve between A and B. And we can shade that in with yellow now. However, because it is a closed bounded interval and it is a continuous function, we know that we have an absolute maximum y value on that interval. On this picture, the maximum y value is here. If I were to draw a horizontal line at that height only over the interval from A to B, and then take the area of that rectangle, it would be greater than the area under the function. There also has to exist an absolute minimum. The absolute minimum, let me go ahead and shade the larger area. Absolute minimum actually occurs at the left endpoint. And again, if I find the rectangle with that height and the width b minus a, the area is smaller than the area under the function, which is smaller than the area under the maximum. Because b is to the right of a, I know b minus a is positive. So I can then divide all three parts of the inequality by the positive value of b minus a. This tells me that the minimum value is less than or equal to 1 over b minus a times the definite integral from a to b of f of x dx, which is less than or equal to the maximum value. But we know what this is. This value right here is the average value of the function over the interval between A and B. And this tells us that we have this average value between the minimum and the maximum, which means that it has to fit somewhere between the pink line and the blue line. Now, because we have a continuous function, we can also use, in fact, the intermediate value theorem. And the intermediate value theorem says if it's continuous and you have two different values, such as the minimum and the maximum, and you've got a value that's between, then somewhere in that interval, you have a C where it takes on the value between the minimum and the maximum. We used this earlier this semester to prove that if a function was continuous over a closed bounded interval, one of the endpoints was negative and one was positive, that because zeros between negatives and positives had to be a point C between the endpoints where it had an x-intercept. In this case, we're using the same idea, but saying that the average value has to be between the minimum and the maximum. And because it is a continuous function, that value has to be taken on at some point C in the interval. And this proves what we were trying to say, that when you have a continuous function at some and integrable at some point over a closed bounded interval, it does take on the average value. If we look back at our picture up here, I'm going to make a wild guess and guess that the average value is somewhere around, well, maybe a little higher here. And again, we can see that on the curve, there are several places that take on that average value. C1, C2, C3. Let's now move on to example 1, where we're going to find the average value of the function x divided by 2, slanted line, over the interval close 0 to close 6, using geometric shapes, since we have not done the Fundamental Theorem of Calculus Part 2 yet. This is going to give us the area between the curve and the x-axis. Then we're going to find the value of C such that f of C is the average value. So we're going to find the average value, which is the y value. We're going to find where it occurs, which is the x value, C. Looking at this function, we can see that we have a right triangle. So let's go ahead and write down what our definite integral would be. Our definite integral would be the integral over the closed bounded interval from 0 to 6 of the function x over 2 integrated with respect to x. Using geometry, I know that this is going to be 1/2 the base of the triangle times the height of the triangle. The base of the triangle is 6 units long, and the height, the perpendicular height, is 3. This gives me 9 square units of area. Then I can use the formula for the average value in order to find what that average y value is. Remember that the average value is 1 over the width of the interval times the area on the interval. We already know that the area is 9 square units, and b minus a is 6. So we have 1 over 6 times 9, which gives us 3/2. In other words, coming here to 3/2 and drawing a line, we have a rectangle that has the same area under it as does the green triangle. And if you notice, you actually get two smaller right triangles here and here, and they're equivalent to each other. In other words, if you cut this one off and flip it upside down and paste it here, it will complete the rectangle totally. Now, the last thing we want to do is we want to find where this occurs. We can see that it's right here, but is it exactly there? We need to figure that out. We know, for example, that this value right here has to be our C value. C is the X value that when we substitute it into the function, we get the average value, which in our case is 3/2. This then tells me that the value of C has to be 3. We have the point 3 3/2 on the function. The value where the average value occurs is at x equals 3. Let's look at another example. In this example, we're given the definite integral of the function 2x squared minus 1 from 0 to 3 is equal to 15. We'll learn in just a few minutes how to compute that ourselves. We want to find the C, the location, such that f of C equals the average value of the function 2x squared minus 1 over the interval from 0 to 3. Now, looking at this area here, we can see that the function is graphed. We have some positive green area above the x-axis and some negative purple area below. And again, what we're getting is net area. We want to find the y value that gives us the average height of a rectangle with the same area as the combined area of the green and purple. And then we want to find the x value where that occurs. Now, in order to do this, we're going to go ahead and we're going to write down the formula for the average value. Average value again, which of course is an y value, is equal to 1 over b minus a times the definite integral from a to b of f of x dx. We know what the value of the definite integral is. We're told it's 15. Our interval is 3 units wide. And this tells us that we have 5 as the average y value. That's the average height. Now we can come here and we can draw a line at height 5. And if I were to shade this in yellow, the area of the yellow rectangle is equal to the combination of the positive area in green and the negative area in purple. I can see that this clearly does touch the function here, but I don't know exactly what that value is. So I want to locate it. But it's on the function 2x squared minus 1, which means that I can substitute in place of the variable c. This is going to give me 2c squared minus 1. But I know that the y value there is 5. Then I can solve for c to get c squared equal to 6, or c squared equals 3, which gives me c is plus or minus the square root of 3. However, the negative root of 3 is not in the interval from 0 to 3. It's not the c I'm looking for. The one I'm looking for that's in the interval from 0 to 3 is the square root of c, or 3. And that means that here on the graph, we actually have the point square root of 3 5. I do have a picture of this, which I'll show you now, so that you can see the related areas on a better than hand-drawn graph. So here's our point, root 3, 5, and you can see the area between the x-axis and the curve, x squared minus 1. This rectangle shaded in light red is the same area as the combination of the green and the purple. It's now time to go ahead and talk about the Fundamental Theorem of Calculus, part 1. Part 1 is the part that deals with the integral and antiderivatives. When we're looking at this, keep in mind that anything called the fundamental theorem of has to be pretty important. In fact, it's the most important theorem in calculus. This is going to give us the relationship between differentiation and integration. And we're going to learn ways to find the value of the area between the curve and the independent axis without using Riemann sums or calculating areas of geometric shapes. We have 2 parts to the fundamental theorem. Part 1 is the one we begin with. It is the one that we use less often, but again, it's foundational to proving some of the later theorems. We start, as we often do, with a continuous function over a closed bounded interval from A to B. We're going to define the function uppercase f to be the antiderivative of this function. F of x is actually defined, and note the weird notation here. This is not an indefinite, so it's not exactly the antiderivative, and yet it sort of is. When we're looking at this, you want to notice several things. First off, the a at the bottom is a constant. It's a constant value that has to be known. Next, you'll notice that the variable used in the upper limit of integration and inside uppercase f is the same variable. In fact, that is the independent variable. The t that appears inside of what looks like a definite integral is in fact a dummy variable. So the t that appears in the integrand and the t that appears in the differential is a dummy variable. It will show up in the middle, but it won't be present in the final product. We're going to state that, in fact, the derivative of uppercase f does give us lowercase f, making uppercase f, by definition, an antiderivative function for lowercase f. As I said, it is an antiderivative, but the form of this particular integral looks more like a definite integral, with the exception that we do not have a constant value for the upper limit of integration. When we say that the derivative of uppercase f is equal to the function, we can say then that this must be the derivative of this integral from a to x of f of t dt. The result is that we get the inside function, the integrand, with the independent variable in the antiderivative and used in the upper limit of integration substituted inside, multiplied by, in effect, the chain rule, the derivative of the upper limit of integration, which will involve the independent variable. In our case, it was just x, and the derivative of x with respect to x is 1, so we simply get the lowercase function f of x. Keep in mind that there will be occasions when the upper limit of integration will not simply be x, it may be an expression involving the variable x. In other words, it could be something like x squared, or negative x, or 3x minus 4. And then we would have to multiply by the derivative of that function using the chain rule. That means that if lowercase f is a continuous function over the interval from a to b, and we define the antiderivative function, uppercase f of x, to be the integral from a constant value a to some expression involving the independent variable in the antiderivative function of f of t dt, then what we do instead is we take the integrand function and we go ahead and replace it with the upper limit of integration and multiply by the derivative of that upper limit of integration. Remember, this is the definition of the antiderivative function, and the derivative of it is what we are computing down here. The derivative of the antiderivative gets us back to f of u of x du dx. Let's make a couple of notes about this fundamental theorem, part 1. For each value of x, let's suppose that we chose an x value, that a was 1, and we chose x to be 10. Then that integral that we define the antiderivative function to be would have a single value for that value of x equal to 10. If I let x instead be 11, I would get a different real value. If I substitute an actual constant in place of the variable x, then it becomes a normal definite integral and gives me the area between the curve of lowercase f and the independent axis. It's still a single finite real number, even though the upper limit of integration is keeping it as a variable expression of the independent variable. If I did substitute for x a single value, I would get a different area. This also implies that any integrable function must have an antiderivative. If we can integrate that, and it's equal to an antiderivative function, which it is because uppercase f, when we take the derivative, gives us lowercase f, then we must be able to find an antiderivative for any integrable function. And in particular, all continuous functions must have an antiderivative. Again, continuity is such an important condition of a function. If a function is continuous, it does have an antiderivative. Let's go ahead and prove the fundamental theorem of calculus part 1 now. Again, what we're trying to prove is that the definition of uppercase f, an antiderivative of lowercase f, is going to be the integral from a constant value to a variable expression involving the independent variable of lowercase f of t dt. We're going to start with the definition of the derivative. We are assuming, of course, that f prime of x has a derivative and it's equal to lowercase f. When we take the derivative, we can use the x plus h format to write it as the limit as h goes to 0 of uppercase f of x plus h minus f of x, all divided by h, way back to chapter 3. Then we can use the definition that we set for that function f of x. The first thing we do is we factor out the 1 over h. That gives us f of x plus h minus f of x inside parentheses. We defined this antiderivative to be the integral from a to a variable expression of x of f of t dt, the lowercase function. We can then rewrite f of x plus h as the integral from a to x plus h. Notice it is an expression involving the independent variable of f of t dt. And we can rewrite f of x as the integral from a to x of f of t dt. In the next step, we can use the properties of integrals to rewrite this last expression. What we want to do is we want to reverse the limits. When we're looking at this expression here, we want to reverse the limits in the second integral. So we're going to rewrite this one instead of from a to x, instead from x to a. But switching the limits of integration adds in a -1 to the integral. A double negative will make it positive. Now, when you look at this, it may be a little bit confusing because the order is a bit backwards. So I wrote it forwards for you here. We have a property of integrals that says if I have the integral from x to a plus the integral from a to x plus h of the same integrand, then I can combine them since the a's are the same constant and rewrite it as the integral from x to x plus h of f of t dt. And I get the expression that you see here. Now, if we're looking at this, the weird thing is the interval over which this one is being evaluated is from x to x plus h. If I were to find b minus a, this would become x plus h minus x, which equals h. In other words, the 1 over h times that integral is actually the average value of the function over this small interval from x to x plus h. This part right here represents the average y value on the interval from x to x plus h. Now we can apply the mean value theorem for integrals. And it says, well, in that case, there must be a c in that interval such that f of c is the average value over that interval. Now, we know that h is going to 0 as we take the limit. Keep in mind that as h goes to 0, x plus h gets closer and closer to x. And since c is between those two values, c must also be getting closer to the value of x. As h goes to 0, c must approach x. Because it is a continuous function, that means that the function exists, the two-sided limit exists, and they're equal. This tells us that the limit of f of c as h goes to 0 must be the limit as c approaches x of f of c, which is f of x. Finally, we can write that the derivative of the antiderivative, which is the limit of the difference quotient, which became the limit of the average value over the interval from x to x plus h, which becomes the limit of f of c, that average value, must be equal to f of x. And this is what we were trying to prove, that f prime, the derivative of the antiderivative, gives us back the function. Let's go ahead and see how to apply the Fundamental Theorem of Calculus Part 1. In this example, we have a function g of r, G of R is the antiderivative function. It's our uppercase f. It's set equal to 0 to r of the square root of x squared plus 4x dx. X squared plus 4x under the square root is our lowercase function, f of x. In order to find the derivative of g, I need to take the derivative of the integral. The derivative and the integral are inverse operations of each other. So when I find g prime of r, that's the derivative with respect to r. It must be r because g is a function of r. The variable used in the upper limit of integration is also r. That makes r the independent variable, not x. In this case, the x is a dummy variable. When I take the derivative of that integral, I can apply the fundamental theorem of calculus. The reason I can apply it is because I have a constant for the lower limit of integration, 0, and an expression involving the independent variable as the upper limit of integration. It is important for fundamental theorem part 1 that the constant be the lower and the expression involving the independent variable be the upper. Now, by the definition, this is going to give me that function that you see on the inside, which is x squared plus 4x. But instead, I'm going to replace what's on the inside with the upper limit. This means that I'm going to set it equal to r. And then I have to multiply by the derivative of the upper limit of integration. The upper limit of integration, the derivative here would just be 1. Substituting r in place of the variable, I get r squared plus 4r. This is the derivative of the antiderivative function. What if the lower limit is not a constant? If this weren't a 0 or a 1 or a 5, but instead was also an expression involving the independent variable, what would I do? Let's look at one so that we can see how this is handled. In example 4, we have the derivative of the integral from negative x to x of t squared plus t dt. T is a dummy variable. The independent variable is x. In order to be able to find the derivative of this integral, what we have to do is split it into two integrals. The fundamental theorem of calculus part 1 only applies when the lower limit is a constant and the upper limit is an expression involving the independent variable, here x. That means that we have to rewrite this one. Between negative x and x, we can choose any constant we want. We don't know what negative x goes to, and we don't know what x goes to. So we can choose any arbitrary constant. 0 is often a good choice. Just habit, I guess. In other words, we're going to rewrite this integral part, leaving the derivative on the outside, as the integral from negative x to whatever constant we choose of the integrand, integrated with respect to the dummy variable, plus the integral from the same constant up to x. And this is one of the properties of integrals that we're exploiting here. I chose 0, but you can choose any constant that you want. Now, in order to apply the fundamental theorem of calculus part 1, this first integral has to be rewritten so that the 0 is the lower limit of integration and the negative x is the upper. But we know how to do that. We switch the limits by introducing a -1 as a factor. This now gives us an integral to which we can apply the Fundamental Theorem of Calculus, Part 1. Because we have the sum of two integrals, and the derivative of a sum is the sum of derivatives, I can split it into the derivative of the first integral plus the derivative of the second. And in fact, I can factor this -1 on the first integral out of the derivative. That's a derivative property. Now I can go ahead and apply the Fundamental Theorem of Calculus Part 1 with the chain rule. This means I take the integrand and I evaluate it when t is equal to the upper limit of integration, -x, multiplied by the derivative of the upper limit of integration, -x. The second one is going to again give me the integrand, t squared plus t, evaluated at the upper limit of integration. Substitute that in place of the variable t. And then we multiply by the derivative of the upper limit of integration, which in the second one will just give us a 1. Once we substitute each of these values into our expression, we end up with a negative, the negative we factored out of the derivative, times the quantity -x squared plus a -x, and then times a -1 from the chain rule. When we simplify, we get the final expression that it is 2x squared. The derivative of that integral is a function 2x squared. Some students wonder why, when we substitute, we only substitute in the value of the upper limit of integration. Why don't we substitute in the lower one? If we were going to substitute in the lower one, and then we take the derivative, well, they just go away. So it's not necessary to substitute in the lower limit of integration. Let's try another example, this time where the expression involving the independent variable is not just x or -x. We want to use the Fundamental Theorem of Calculus Part 1 to find the derivative of the integral from x squared to 10 of 1 over t squared plus 1 dt. Again, t is a dummy variable. The independent variable is the one in the derivative and the one in the limit of integration, x. First, we have to reverse these limits of integration because the variable involving the independent variable is in the lower limit and it needs to be in the upper. We switch the limits of integration, which introduces a negative. The negative can be factored out of the derivative. Then we go ahead and apply the fundamental theorem. We take the integrand. Keep in mind that the integral is undoing the derivative, and then we're doing the derivative again, so it doesn't change the integrand. We get the integrand, but we're going to substitute in place of the dummy variable t, the expression x squared. Then we have to multiply by the derivative of that expression in the upper limit of integration. That's the chain rule part. This gives us -2x over x to the 4th plus 1. Be sure that you don't forget to apply the chain rule and multiply by the derivative of the upper limit of integration. Let's now look at example 6. I would like you to work this one out on your own. So pause the video now, work it out, then turn the video back on, and we'll compare our results. Again, we check to make sure that we can apply the Fundamental Theorem of Calculus Part 1. We check that the lower limit of integration is a constant and the upper limit of integration is an expression involving the independent variable. Independent variable is indicated by the derivative on the outside and the presence of the x in the upper limit of integration. The t that appears in the integrand and differential are dummy variables that will disappear in the final result. Then the derivative of the integral from 1 to x cubed of cosine of t dt. Remember, the integral is doing an antiderivative, and then the derivative undoes it. So we get right back to cosine of t. But we're going to substitute the upper limit of integration, which is x cubed. Then, applying the chain rule, we have to take the derivative of that upper limit of integration, x cubed, giving us the result 3x squared times the cosine of x cubed. It's now time to cover the Fundamental Theorem of Calculus, Part 2, the evaluation theorem. This is the one that truly changed the world. This is the one that you will use on a daily basis from now on. In fact, as you progress into Calculus 2 and Calculus 3, it's part of many, many problems, if not 85% or more. Integration is one of the fundamental uses of calculus. The Fundamental Theorem of Calculus Part 2 is the way that we're going to relate the indefinite integral antiderivative function to the definite integral, the area between a curve and the independent axis. In other words, the fundamental theorem puts these two very different types of integrals together and relates them. We're now going to be able to calculate the area between a curve and the independent axis without having to resort to a Riemann sum or some kind of geometric shape. We won't have to approximate. We'll be able to integrate directly using the Fundamental Theorem of Calculus, Part 2. It's actually a relatively straightforward statement compared to the Fundamental Theorem of Calculus, Part 1, which is far more complicated. We again start with our very typical condition that f of x be a continuous function over a closed bounded interval from a to b. We let uppercase f of x be any antiderivative of the function lowercase f of x. Then we state that the definite integral from a constant a to a constant b of f of x dx is equal to that antiderivative evaluated at the upper limit of integration minus the same antiderivative function evaluated at the lower limit of integration. In other words, the area under the function lowercase f of x between a and b is the difference in the antiderivative function evaluated at the endpoints. This makes our work far, far simpler. We often use that vertical bar notation that you saw me use when I was applying it in examples for the Fundamental Theorem Part 1. We often will put a long vertical bar, but in this case, we're evaluating not just at the upper limit of integration, but at both. So we put a at the bottom and b at the top, and we write the antiderivative function f of x evaluated between a and b. Again, it's going to be evaluated at the upper limit minus the evaluation at the lower limit. This says we can take any antiderivative of lowercase f and use it to find the area between the curve and the independent axis. Now, when we're doing this, it won't affect the answer no matter which antiderivative function you take. This sometimes confuses students since they know the antiderivatives are only good up to a constant. They all have a plus c. The reason why you get exactly the same answer is, let's suppose your c was plus 5. When you substitute the right endpoint into your antiderivative, you'll get a plus 5 on the end. Since it was a constant, there's no place to plug in the b. When you substitute in the left, you'll also have a plus 5. But this one's being subtracted, which gives you 5 minus 5, which is 0. The constant will always cancel out, no matter what it is. In which case, it makes more sense to use the simplest antiderivative function we can, which is the one where the plus c is 0. Even if it's not, it will cancel out. But it is our habit to choose the antiderivative where c is 0. Let's go ahead and prove this fundamental theorem of calculus, part 2. We're going to take a regular partition of the interval from a to b. This will give us values for x sub k that are the endpoints of the subintervals. X sub 0 or x naught will be a, and then we'll have x1, x2, x3 up to x sub n, which is equal to b. We're going to write the difference between the antiderivative evaluated at b and at a by rewriting b as x sub n and a as x naught. And then we're going to apply, well, sort of a trick. We're going to add 0. What we're adding in here is the other interval endpoints between the first one and the last one. So I subtract the antiderivative of x sub n minus 1, and I add the antiderivative at x sub n minus 1. Since I'm adding and subtracting the same thing, I've added 0, which means I haven't changed it. I do this for every single x sub n between 0 and n. When I'm done, what I'm going to do is rearrange these. So I'm going to reorder them, and I'm going to group these two together, and then these two together, and the next two, and so on, all the way down to the end. When you group them together, notice this gives you f of x sub n minus f of x sub n minus 1. This would be the antiderivative evaluated over a small subinterval. And the next one is f of x sub n minus 1 minus f of x sub n minus 2. Again, evaluating over a small subinterval. This is just a rearrangement of terms, so it is equivalent to f of b minus f of a. Then we can rewrite this using summation notation as the sum from k equals 1 to n of f of x sub k minus f of x sub k minus 1, which will give us all of the ones that you see here. Now, we know that uppercase f is an antiderivative function of the lowercase f over the interval from a to b. By the mean value theorem, the regular one, we know then that it has to be continuous since it's differentiable, and we know that it has a derivative. In that case, then in each subinterval, there must be a point where the slope of the secant line is equal to the slope of the tangent line. Remember again that when we write something like this, we are computing the slope of the secant line. According to the mean value theorem, there has to be a c sub k in this kth interval between x sub k and x sub k minus 1, where the slope of the secant line is equal to the slope of the tangent line. In other words, the antiderivative's derivative at c sub k is equal to the slope of the secant line. And then we simply move the denominator to the other side to get the antiderivative's derivative at c sub k times x sub k minus x sub k minus 1. this becomes delta x. But the derivative of an antiderivative gives me back the original function f. So this gives me lowercase f at c sub k times delta x. Now we're going to substitute the right-hand expression in for the left-hand expression. F of b minus f of a, which was f of x sub n minus f of x naught. Then we added zeros. Then we regrouped. Then we can replace each of these pairings with the summation from f of x sub k minus f of x sub k minus 1. And that can be replaced by the summation of the lowercase function at the mean value theorem, where the slope of the tangent line equals the slope of the secant line over the subinterval multiplied by delta x. Now we want to take the limit of both sides of this equation. What we have right now is f of b, the antiderivative function, minus the antiderivative function at a, equal to the sum of the lowercase f times some point in each interval times delta x. You should recognize what this is. It is a Riemann sum. If I take the limit of both sides as n goes to infinity, or equivalently as delta x goes to 0, well, when I take the derivative or the limit of f of b minus f of a, these are both constants and they don't depend on n. So the limit of a constant is the constant, which just gives me the antiderivative at b minus the antiderivative at a. Here, though, I'm taking the limit of a Riemann sum. C sub k is a point in the kth subinterval. By the definition of the definite integral, this is the integral from a to b of f of x dx. This is what we were trying to prove, that the definition of the definite integral is the difference in the antiderivative function evaluated at the endpoints of the interval. Let's see how to apply the Fundamental Theorem of Calculus Part 2. You're going to become experts at it because you simply can't do calculus if you're not. This is going to have to be at, well, above the 95% level. Looking at this problem here, we have the integral from 1 to 2 of x to the negative 4 dx. We need to find an antiderivative function, any antiderivative. This is how we're relating the indefinite integral, which gives us an antiderivative function, with the definite integral, which gives us the area under the curve. We can apply the power rule for integrals. Remember that this means we add 1 to the power and we divide by the new power. We want to evaluate this between the limits of integration 1 to 2. This means that we're evaluating x to the negative 3 divided by negative 3 between 1 and 2. You can, if you want, factor out the negative 1/3, or you can leave it there. You could also rewrite this as 1 over negative 3 x cubed, which might make it a little bit easier to substitute values. At the upper limit of integration, this becomes negative 3 times 2 cubed minus 1 over negative 3 times 1 cubed. Notice that the minus here is from the Fundamental Theorem of Calculus Part 2. It's the minus between the antiderivative at b and the antiderivative at a. This one was a part of the antiderivative function, which is 1 over negative 3 x cubed. Evaluating this gives me 8 times 3 which gives me a -1/24. And the one next to it, I have a double negative, which gives me +1/3. Then I can get a common denominator between the two by multiplying by 8/8. This gives me 8/24 minus 1/24, which will give me a final answer of 7/24. The area under this curve between 1 and 2 is 7/24 of a square unit. Let's now take a look at example 8. When we look at example 8, we have the definite integral from 0 to 1 of the function x minus the square root of x. In order to find an antiderivative function, it will be helpful if you rewrite the square root as x to the 1/2 power. Go ahead, pause the video to work it out, then turn it back on so we can compare our results. First, I split this into two separate definite integrals. As you become more experienced working with the Fundamental Theorem of Calculus Part 2, this step is not actually necessary. You can keep them together, and you can simply find an antiderivative function for the whole thing. For now, I went ahead and split them apart. I rewrote the square root of x as x to the 1/2 power. Then I applied the power rule on each integrand. This gave me x squared over 2 to be evaluated between 0 and 1, and x to the 3/2 divided by 3/2, which makes it 2/3 times x to the 3/2 between 0 and 1. There was a subtraction between the terms, so it's still there. In the next step, you'll see that I actually factored the constant off before I substituted in the limits of integration. This often can make life simpler when the constants are fractions. So I substituted 1 in place of x to get 1 squared minus 0 squared, which is just 1, so I get a 1/2. In the next one, I factored off the -2/3, and then I took 1 to the 3/2 minus 0 to the 3/2, which again is 1, giving me -2/3 and a final answer for the area under this curve, or rather between the curve and the x-axis, from 0 to 1 of -1/6 of a square unit. Let's take a look at the graph so you can see what it looks like. The graph of it is right here, and you can see that it is in fact below, which accounts for the reason that it came up negative. In this case, 1 square unit would be from here around to here, and it does look like it's about 1/6 of that block. Let's take a look at example 9. In example 9, we have an integrand of sine x plus cosine x. And we're integrating from -π/4 to 7π/4. Go ahead and pause the video and apply the Fundamental Theorem of Calculus, Part 2. In this problem, I chose not to split it into two separate definite integrals. Instead, I kept it together and found the antiderivative of each term individually and kept them together. Remember that to get sine, you took the derivative of a function and it turned into sine. That function must be negative cosine of x, the antiderivative of sine. The function whose derivative gives me cosine is sine x, the antiderivative of cosine. This needs to be evaluated between -π/4 and 7π/4. Notice that I substituted the upper limit of integration into the antiderivative function. Notice I chose that my constant was 0. This first part represents the antiderivative at b, 7π/4. The second part, notice, is all in parentheses because I'm subtracting all of the antiderivative at the lower limit of integration. The parentheses are necessary. When I evaluate the sine and cosine, remember that 7 pi over 4 is found by going counterclockwise 7 pi over 4 units, which puts you halfway through quadrant 4. When you evaluate negative pi over 4, starting from the positive x-axis, you simply move backwards 1 pi over 4 and end up in the same location, which means that when we substitute these in, get the same value, but because of the subtraction, they cancel. What does that tell you about the function and the area between it and the x-axis? That's right, it's got to be the same amount of area above as there is below. And you can see in this graph here, graph between negative pi over 4 and 7 pi over 4, that the area above the axis is equivalent to the area below, which is why we got 0 area. Let's now look at example 10. Go ahead and pause the video and work out example 10, then come back so we can compare. So it was short, wasn't it? Remember that an antiderivative of e to the x is e to the x. In that case, we choose the constant to be 0 just for less work, and we evaluate between the limits of integration. Substituting the upper limit in place of the variable x, I get e to the natural log of 8. Remember that the exponential function and natural logarithm are inverse operations, and they're touching back to back without a constant outside the natural log, and they undo each other, and I simply get 8. Then I have to subtract the evaluation of the antiderivative at the lower limit of integration, which is 0. E to the 0 is not 0, it's 1. And that gives me 8 minus 1, or 7 square units. Let's take a look at the graph and see if we agree that it looks like 7 square units. On the graph that you see here, a square unit is 1, 2, 3, 4, 5. Okay, it's one of these little blocks here, and I've got clearly 1, 2, 3, almost 4, little 5, 6, and some more. Yes, I believe it. It could be 7, and it is definitely above the axis, so it is positive. Let's now revisit our average value using the Fundamental Theorem of Calculus Part 2. Remember that the average value is given by the reciprocal of the width of the interval multiplied by the definite integral, the area between the curve and the independent axis. Now that we have this definition to evaluate the definite integral, we can find the average value for functions that don't lend themselves to geometry. Let's take a look at one here. We're going to use the Fundamental Theorem of Calculus Part 2 to find the average y value of the cosine function over the closed interval from negative pi over 2 to pi over 2. The first thing that we have to remember is what the formula is. The average y value is given by the difference in the endpoints times the area between the curve and the independent axis. That means that our average value is going to be 1 over pi over 2, our b, minus a negative pi over 2. The double negative will give us a positive, so we'll get 2 pi over 2, which becomes 1 over pi. And we want to multiply by the integral from negative pi over 2 to pi over 2. Our function is cosine of x, and we're integrating with respect to x. Remember that the variable that you use in a definite integral is actually a dummy variable. I could have written cosine of t dt, or cosine of happy face d happy face. It won't affect the fact that the independent variable is still x. let's now find an antiderivative function for cosine. An antiderivative function for cosine is sine. Then we evaluate between the limits of integration. And I got those a little too close together. Coming over here, I'm going to leave the 1 over pi outside as a constant factor. It's a fraction, and this will make my work easier. And I substitute the upper limit of integration into the antiderivative function and subtract what I get when I substitute the lower limit of integration into the antiderivative function. The sine of pi over 2 is 1. The sine of negative pi over 2, remember you're going backwards, is going to be actually the same as the sine of 3 pi over 2, which is a negative 1. But I have subtraction in the middle. 1 minus a negative 1 gives me 2. That tells me that my average y value is 2 divided by pi. Let's now take a look at this particular function so that we can see what it looks like. Here's the graph of cosine between negative pi over 2 and pi over 2. I've shaded the area under it in a light gray. The average value is 2 divided by pi, which is graphed here also between negative pi over 2 and pi over 2. The area of that green rectangle is exactly the same area as in the gray shaded region under cosine. That's the purpose of the average value. We have one more problem to work, which is example 12. On example 12, I would like you to pause the video and work this one out, then turn the video back on so we can discuss. When we evaluate the average value, remember you're multiplying by the reciprocal of the width of the interval. Since our interval is 0 to 2, that means we're multiplying by 1/2. Our function is e to the x, and an antiderivative of e to the x is e to the x plus 0. Of course, e to the x plus 2 would also work. Then we're going to evaluate between the limits of integration. We substitute these in. I keep fractional coefficients outside to make my work easier. There are multiple ways of writing this. You could also write it as e squared minus 1, all divided by 2. It comes out to be about 3.2, which is the average y value. The y value whose rectangle over the same interval gives you the same area that's between the curve and the axis. Let's take a look at it now. When you look at this, realize that the exponential is graphed here in orange and it turns dark on the inside. The area between 0 and 2 under the curve is shaded a light gray. Then I drew a horizontal line segment over the interval at the height of our average value, e squared minus 1, the quantity divided by 2. The area in green is equivalent to the shaded gray area. They're exactly the same. This is the end of the video on the Fundamental Theorem of Calculus, a truly miraculous discovery. In the next video, we'll talk about the net change theorem and some integration formulas. We'll also talk about what happens with even and odd functions when you integrate over a symmetric interval on both sides of the origin. I hope you'll join me for the next video.